Hi, and welcome to Dr. V's Chemistry Webcast. Today we're talking about accuracy and precision. Now, these are terms that are used a lot in science classes, and we need to know what they mean. The other thing that I wanted to accomplish today is that we spent a lot of time talking about measurements and sig figs and how to treat sig figs and calculations, and these really come back to these ideas of accuracy and precision. So I'm hoping we're going to pull some of this together. So there's no such thing as a perfect measurement. All measurements have some error. We have that estimated digit. There's instrument errors. The method may not be appropriate. You just make mistakes sometimes. There's no such thing as a perfect measurement. They all have error. Now, you're not going to talk about human error when you go to write about lab reports, but there's still going to be an error in every measurement. Perfect doesn't exist. We can have systematic errors. And what I mean by a systematic error is that they're consistent errors. They're built-in errors, part of the procedure, that consistently change all the measurements by a certain amount because you didn't quite do something correctly. Like I said, they're consistent and repeatable, and that means we can predict how this error will affect the magnitude of the measurement. For example, if I want to measure the length of a piece of fabric and I have a measuring tape, but my measuring tape was stretched out and I wasn't aware of it. So my yard is longer than a yard. When I go to find the length of my fabric, I'm going to get a reading for the fabric that's smaller than it should be. This is called a scale error. Or maybe I need to measure my height, but I wore my shoes. That's going to give me an offset error. All right, I'm going to get consistently height measurements that are too large because I've got my shoes on. Another example is I'm trying to find the mass of a sample on a balance, but I either didn't zero the balance correctly, or I didn't calibrate the balance, or if maybe the sample was held in another container and I didn't account for the mass of that. So we can have different offset errors here as well. But these are systematic errors, and I can predict, this particular error will make my mass too big, and this would make it too small, etc. We can also have random errors, and as you might imagine with a random error, they're kind of unpredictable, and it's not something you can know in advance what effect that would have on the magnitude of your measurement. And these can relate to the limitations of the instruments if you're working right at the smallest things that instrument can measure, or if you have tiny variations in the procedure, this could give very small changes in your values. For example, the room temperature might fluctuate. Maybe you're trying to measure something about a gas sample and its volume. Well, that would change considerably with temperature as the temperature is fluctuating. If you're trying to measure the volume in a graduated cylinder or in a burette, and you're at a slightly different angle each time. So one time you're looking up at it a tiny amount, the next time you're looking at the meniscus down a little bit, it's going to give you very small errors maybe in your reading. And it's going to change the effect each time. So that's hard to compensate for. Or if you're trying to find a mass of a sample on a balance and there are air currents in the room, those air currents can be making the mass reading appear to go up and down on the balance, and it makes it hard to know what the correct reading is. But it's also hard to say, is it making it too big? Is it making it too small? We've got errors in both directions. So let's talk about accuracy. Accuracy is all about the right value. Did that measurement approach the true value of that quantity? All right, how close am I to the accepted or true value? So when we're talking about accuracy, we might be talking about percent error is one way we can talk about this. Precision is not the same thing. Precision, when we're talking about it in a scientific sense, how refined is that measurement? How reproducible is that measurement? That's really what we're focusing on. They're both precision and accuracy are discussing the quality of the measurement, but they're talking about two different things. So precision can talk about reproducibility. So if we have some rulers with different markings, all right, the significant figures reflect the precision of those markings, right? So a ruler that's only marked every 100 centimeters is not going to be as precise as a ruler marked every 10 centimeters, which certainly is not going to be as precise as a ruler marked to every centimeter. Okay, and so the sig figs actually tell us the scale markings of the instrument, and we can go back and forth with that, right? And so if we have finer and finer and finer divisions for the scale markings, I'm going to have more sig figs for that measurement, and that's going to be more precise. All right, and so that can be a useful thing. But precision can also be interpreted in a different way. We can also talk about precision in terms of how far are we from the mean or the average if we have a whole set of measurements. All right. So the range of a set of measurements in a set is another way to discuss precision. All right. If I have a larger range, it's not as precise. And if I have a smaller range, it's more precise. So let's look at experiment 1. I have trials A, B, and C, and I'm measuring the mass of a sample. You can see that they're all pretty close together, and the range is 0.05. In another set of experiments, trials X, Y, and Z, I've got actually the same average for the masses if I were to add them up and divide by 3, but I have a much larger range for trials X, Y, and Z, which is saying that these trials this set of data is less precise than trials A, B, and C are collectively. All right, so that's another way we can think about range. So we can also think about accuracy and precision from a visual standpoint, and sometimes this can be very helpful for students when they're seeing it for the first time. So if we have good accuracy, we're going to be very, very close to the value that we expect. And good precision means they're all clustered closely together. So if the bullseye represents the accepted value or the true value, right, good accuracy, all my data points would be right on the bullseye or very, very close to it and clustered very tightly together. Okay. If I've got good accuracy but poor precision, on average, it would come out to the bullseye. But there's going to be more scatter. All right. So, if I were to take the mean, they come out very similar and they're right in the range where I would expect them. But you see there's a lot more variability here. So this is less precise than my previous example. If I have precise data that's not accurate, they're very tightly clustered, but they're not near the accepted value or the expected value or the real value for the measurement. All right. Obviously, that's not great either. And we can have data that's neither accurate nor precise. Certainly, we don't want that. All right. Where they're scattered and the average is nowhere near what it should be. So we have different ways of thinking about accuracy and precision. So to wrap this up, this is an assignment for my class. You and your classmates had to measure the length of a pencil in centimeters. I want you to make up data sets. You're going to make up 4 data sets. One where the data is accurate but not very precise. Another where the data is precise but not very accurate. A data set where it would reflect both accurate and precise data, which is obviously the goal of any measurement. And then a data set that's inaccurate and not very precise. You're going to have your 4 data sets. You can tell me what the length of your pencil is, and you're going to write this out or do it on your computer and take a screenshot of this and upload it to the assignment in Google Classroom for my students. Okay, and this is a good practice for you. Do you understand what these mean? And we'll talk about this next time we meet in class.